someone came to join me. This is Marshmallow. He says hi. He's very soft and fluffy, and he's he's a lump of fluff, but he's very cute. And he likes to come up and annoy me when I'm in calls or running conferences. But our next talk is going to be on code analysis, both dynamic analysis and static analysis. So Sunny Chatterjee and Jim Radigan are going to be telling us about all we've been working on in code analysis and how it can make your C++ better. So welcome, Sunny and Jim.
Thanks, hey.
How's it going?
Good. How are you?
Good. I've got a little friend now, so I'm happy.
That's great.
Thank you very much for your time and joining us, and I'll pass it over to you.
All right. Bye. Hey, everyone. My name is Sunny Chatterjee. I'm an engineering manager in the C++ team at Microsoft, where I'm lucky enough to work on static analysis. And today I'll be joined by Jim Radigan. Jim is an architect in the C++ team, and we'll show you how you can use code analysis to empower developers, write performant, reliable, and safe C++. Hi, Jim. All right, looks like you're muted there.
Good morning.
All right. I'll cover the topics for today's talk. First, I'll go over why code safety matters. And then I'll talk about how you can improve code safety using static analysis principles. And Jim will go over how you can use address sanitizer to improve the safety of your code. So why code safety matters? So in 2020 State of Quality Survey, developers were asked what sort of analysis tools they are investing in to improve the reliability and safety of their code, essentially making their code safe. And both static and dynamic code analysis tools topped that list. So the challenge for us was to see if we could leverage the code analysis tools that we work on here at Microsoft to make C++ a safer language. So in this section, I'm going to focus mainly on static analysis and how you can improve the safety using static analysis principles. So what is static analysis? It's a pretty simple technique that reads C++ code, applies some clever algorithms to look for defects, and reports these defects at compile time. And so why static analysis is a pretty popular technique is because it can drive your quality upstream, where you can find bugs at the very beginning of your development cycle. And that saves a bunch of dollars for the company. And large corporations, they love it when people can save dollars, right? So it has been in use in many large corporations over the years. It has a pretty minimal overhead in terms of there's no instrumentation needed. There are no test cases that you need to write. And it has, a pretty strong, it has a proven track record in finding a pretty wide range of issues in your code, ranging from correctness, performance, reliability, safety. So you can find all these issues using static analysis. Next, I'm going to show you a few good checks. For long, people have thought about static analysis as Lin-style checks. And what I'm going to show here in these examples is, static analysis has evolved over the years, and you can find a lot of deep semantic errors in your code using it. And it's a lot more than a classic Lin-style check that you would expect it to be. So here is an example where you have a function unchecked index. It takes a vector, a reference to a vector. Then you get an index from the while. So you don't know anything about the range of that index. There's a function called getIndex that gets you that index. And then you're basically dereferencing into that vector, but you don't know whether you'll be accessing that vector out of bounds. So it's a pretty simple check to write here, where that would say, use GSL add instead of unchecked iterator. Now, GSL add, for those of you who are familiar with the guideline support library, you know that it's like a function that would terminate your program if you're trying to access this container out of bounds at runtime. So because of that runtime safety, it's a much safer alternative to use. Let's look at a slightly modified example. In this second example, the index is in fact checked, because you can see that if the index is less than the size of the vector, only then we try to access into the vector. And so this is a perfectly valid access. And a smart static analysis tool would be able to, walk these paths during analysis and figure out all the conditions. And so it would kind of be smart about and not warn this particular example. So as you can see that, it's not just a simple lin style check, but there is a lot of deep analysis happening under the hoods to kind of provide you with high quality defects where you actually have a bug in your code. In the second example, I'll show you how you can use static analysis to make your code more performant. So you have some struct here that has a large struct in its body, and it has a method that returns a const reference to that large struct. And then you have a function foo that essentially calls get large struct, which returns a reference. C++, as you know, is a copy by default language. So when it gets assigned to that auto variable, that large struct gets copied. And because of that, there is a lot of, that's not a very efficient way of writing code. So a static analysis tool can help you here and tell you that, hey, there is an expensive copy happening here. You should use a reference. However, let's look at the next two lines. In the next two lines, you can see that we do get a reference and it's copied, but there's also the data inside that struct that's being mutated. So we are writing to its field the value of 43. And so in this case, a copy is in fact necessary. Again, a smart static analysis tool would be cognizant of this scenario and would not ask you to create a reference in this particular case. We need a copy here. The third example is where you're actually calling some struct which returns a temporary object, and you're calling get large struct on that temporary object, and then you're assigning that to an auto variable, which means a copy here is happening. And again, the smart static analysis tool would figure out that the copy here is necessary. Why? Because the lifetime of that temporary object is not extended past its statement. So a reference here would mean that you would run into lifetime issues after this statement. So that's my second example. For my third example, I'll show you how you can use static analysis to prevent concurrency errors. Here is an example function called mutex acquiring generator. It acquires a lock, and as you can see, the variable is marked with a guarded by annotation, which means you should be acquiring this lock before, in fact, you access this variable. Then this coroutine yields its control before it relinquishes that lock. Now, the problem with this is, imagine there is a second thread that picks up this coroutine and then it tries to get that lock. And this would be a classic deadlock where the first thread has return control while holding the lock, while the second thread is waiting for that lock. Static analysis can help you here. It can tell you that, hey, you're suspending a coroutine while holding a lock, and that can cause deadlocks. Don't do that. So this is another interesting example where, as new language features evolve, you can see that you can make mistakes in new ways. And static analysis can be a powerful tool in guiding you in writing code that is correct and safe. My last example is a lifetimes check. Lifetimes, as you know, is a 40-year-old problem, as Herb often refers to it as. And you can use static analysis to also find issues about lifetimes. Here is an example where you have a dangling iterator. There's a vector, 3 elements. You basically take an iterator to the beginning of that vector, and then you're accessing, dereferencing that iterator. And that's perfectly valid code. It should be overriding the first element with 0. Now, let's look at the second dereference here. Here, you're basically pushing back another element onto that vector and dereferencing through that stale iterator again. And that's not OK, because when you do a pushback, the memory layout can change. So that first iterator you had pointing to the beginning of the vector can point to invalid memory. So if you run static analysis here, it can actually point you out that, hey, don't dereference this pointer because it's invalid, and it will tell you further that it's been invalidated in the previous line. So those are a few examples of a few good checks that I wanted to cover today. Next, I wanted to give you a glimpse of how the static analysis platform looks like. Just an under the hood picture here. I'll be quick on this for the scarcity of time, but you have C++ front end. You have the parsers parsing these files. It ensures that it has valid syntax. It produces something called abstract syntax trees or ASTs that represent source code. And then you have something on top of it called prefast. Prefast is this analyze, as you know it in MSVC. basically loads and unloads its own plugin extensions. It calls back to each plugin as declarations and definitions are parsed, and then it also emits defects it gets from its plugins. On top of FreeFast, we have something called ESPX engine. So ESPX engine, what it does is it processes the ASTs to simulate function execution. And the way it does it is by converting these ASTs into something called control flow graphs or CFGs. And as it tries to simulate the function execution, it invokes callbacks on each of its own extensions as the simulation proceeds. So you have one extension which handles its own callbacks of interest. It tracks some properties that it's interested in. It detects errors, and then it reports its defects back to the engine. Similarly, you have a second extension that handles its own callbacks and detects errors and reports them back to the engine. ESPX engine is a pretty powerful platform. It has evolved over the last 10 years through collaboration between DevDev and Microsoft Research. It has a lot of good, useful libraries like symbolic state tracking. It has a fast theorem prover. It has alias analysis, loop widening. All of this makes it a pretty powerful platform to do data flow and path sensitive checks. And a lot of the deep semantic checks that I showed you in the previous slides, they are powered by some of these libraries sitting on top of ESPX engine. I would like to tell all of you to join the fun. My key message today is, we have been using static analysis at Microsoft for nearly 2 decades, and it's validated millions of lines of production C++ code. It's available in all editions of Visual Studio. It's, static analysis finds bugs, it's free, and therefore you should use it. So what's next for the static analysis team? We definitely want to invest in C++ code safety checkers going forward. We also want to be able to meet the tooling needs of the community as the language evolves. So for C++ 20, for example, there were a few interesting types added for static analysis. Standard span would be one of them. Similarly, coroutines was another language feature where you could create new kind of lifetime problems when you're using coroutines. So as the language evolves, there are new ways people can make mistakes, and static analysis tools, any tools for that matter, should be constantly evolving to catch new kinds of defects that you can introduce. We also want to focus on improving our diagnostics. No matter how smart a check you are writing, I think for a tool, diagnostics is very important. You should be able to point out issues in the code that you're writing. The issues should be easily understandable. It should give you a glimpse into what's the reasoning behind the tool. So we definitely want to focus more in improving our diagnostics going forward. And we also want to have a tighter integration with developer workflows. So I think our friends in the IDE team did an awesome job integrating these checks as part of the Visual Studio design time experience. And we also realized that that developers are also spending time in GitHub, they're spending time in Compiler Explorer. So the point here is we would have a static analysis experience available for developers wherever they come for writing C++ code. In the end, I would kind of urge you all to give us feedback and suggestions. It could be about a bug, a feature request, some new checks. We have a pretty active community in developer community. A lot of our prioritization is directly based on the feedback and suggestions we receive there. So I would urge you to keep the feedback coming. For example, if you would like us to, open up the static analysis platform that I just showed you in the previous slide, and if you would like to write your own third-party plugins, that's something you could probably reach out to us and suggest in the developer community. Definitely helps in the prioritization. In the end, I would like to leave you with a few useful resources. Our documentation is at docs.microsoft.com. It's not perfect, but we are constantly looking to improve on it. Feel free to suggest improvements on the documentation and check them out. We also have our team blogs. Most of our announcements are made through the team blogs, and I've just had 2 blogs listed here that highlight some of the work that went into the static analysis tools over the past few months. So definitely stay tuned for our announcements in the C++ team blog. And there is some additional reading that I would like to leave you with. C++ core guidelines is a great resource to check out. It has a whole bunch of rules on how you can write modern, safe code. Uh, and one of our checkers, the C++ code check, implements a whole bunch of rules from this guideline. We also have a guidelines support library. It's a GitHub repo that we maintain where we implement a bunch of type extensions, which are used to enforce some of the core guidelines. So definitely you can engage with us in the GitHub repo by contributing to Microsoft GSL. And we love all sorts of static analysis tools. And for those of you that haven't played with ClangTidy, we have got ClangTidy integrated inside of Visual Studio. Definitely check it out, and you can read more about ClangTidy in the LLVM org. I would like to end with a demo because so far I haven't shown you anything what the experience is in GitHub. Is in Visual Studio. So let me show you an example in Visual Studio how static analysis is integrated. So here is a source file, and you can see these green squiggles sprinkled through the source files. Essentially, what happens is as you're writing and typing your code, static analysis runs in the background, and the defects show up as green squiggles. So if you hover over the squiggle here, it will say, oh, the default constructor may not throw, declare it as no except. Similarly, you have another squiggle here that says, function work with delete can be declared no except. If you have a squiggle here under delete, it says do not delete a raw pointer that is not an owner. For those of you that are familiar with core guidelines, you know that only owners can delete its own memory. And it also says avoid calling new and delete explicitly, use unique pointers, because that way you can write memory safe code. So there is a whole bunch of static analysis issues that you would find available in your project as green squiggles. As you fix them and save your work, they should start disappearing. One interesting thing in this demo is there is a subtle memory bug here that I don't see mentioned by static analysis. And so there is a magic button that I would like to show you. If you go to the project properties here and go to general, there is the drop down, this magic drop down, as I call it, called enable address sanitizer. And all you got to do is flip it to yes and save your project properties and recompile. And once you do that, you will find that address sanitizer is able to find all sorts of subtle memory issues in your code. And to talk more about it, I'm going to hand over now to Jim. And Jim is going to talk about the magic behind this address sanitizer. Over to you, Jim.
Hey, thanks, Sunny. Great job talking about the static analysis. Good morning, everybody. I'm just going to take that same demo that Sunny was showing you. I named it after him. I just wanted to show you the code. So right here, I just added the one-line pass to prove that this thing will actually run. So I'm just going to compile this in an ordinary way. Now I'm going to run it. And you can see that that ran, and that's after you would have taken care of some of these static analysis bugs. What I'm going to talk about is the address sanitizer, which is going to be about dynamically finding these bugs at runtime. So in order to invoke the address sanitizer on exactly the same example that was Sunny was showing you, I'm just going to type cl-f and address. We're going to add some debug information so that the stack walker can handle this when it finds an error. Now, when I run this, we're going to get an error. And the error that's pointed out by the address sanitizer is that there's a new delete type mismatch. And this is the standard output that you would get from the Clang compilers. So what we did is we took this a step further and we integrated this tightly with Visual Studio. So what I want to show you is if I pull this up in the Visual Studio debugger, we'll get what I consider to be an easier read on what the problem would be. So if I just click go, The integration with Visual Studio has popped this error in the window for you. You can actually see that it just says the deallocation size is different from the allocation size. And you can see that it happens exactly right there. And now you have your call stack and all of the information that you would have had from the command line behind this window. But this is a lot easier to read. And so what's happening here is the address sanitizer found out that there wasn't a virtual destructor for the base class that could be overridden. So that's why the delete had a mismatch in sizes for what was allocated, because right down here, we actually put a derived into the pointer B, and then we passed it down to the delete. So now, what I wanted to do was show one more feature that we added for supporting this, which is, I think, really important. You set that environment variable, asan save dumps. What's going to happen is when this thing errors, it's going to save a new type of a dump file that has a whole bunch of asan metadata in it. And the IDE has been engineered to parse that and display it. So if I run this now, same file, it's got an error. But what it's doing is it's saving that dump file. And now I can actually look at that file offline. So if you're doing stuff in the cloud, what you can do is set that environment variable, store all of these dump files in a database, and come back and process them whenever you want, because all of the metadata has been saved, and this can be rehydrated by Visual Studio at any time. So if I just open this file with Visual Studio, one more mouse click, and boom, I'm processing this bug offline. And the number one thing that's really significant about this and these dump files is that this changes the way you would report bugs, because with the address sanitizer, there are 0 false positives. So if you have a bug, it probably is yours. And with this dump file, if you stored this with your bug reporting database, it's extremely accurate. You have memory, you have the registers, you have the call stack and all the symbols and the source code right there. And if you want, you can even go to the disassembly and you can see where the code, where the derived was created, and you can also go to the code for the delete. So with the combination of integrating this tightly with Visual Studio and with creating these dump files, we feel that we've really made the address sanitizer as useful as possible. And the reason for that is that the memory safety issues that the address sanitizer focuses on are dominating what all the CVEs are every year. And as we continue to develop more and more code with C and C++, we continue to introduce these memory safety issues, and it's a really big deal. So if you want to consider this for just basic correctness, the address sanitizer is a big help. Or if you are worried about security and third-party nation states, this is one vulnerability that is constantly exploited. So Sonny was talking about static analysis, and that's meant to be used at build time. That's low overhead and it catches bugs really early, but there's some noise and warnings. The address sanitizer is done at runtime. It requires a separate build. There are 0 false positives, but it finds bugs that any type of static analysis can't find because of cycles in type propagation and alias analysis. So from our point of view, both of these are available under one compiler switch, and together they present what we consider to be a defense in depth. And this is, I think, very covering for a lot of the problems that you see in the industry today, the combination of these two. So why is it that there are things that static analysis can't find? And what I'm going to do is provide 2 key insights to clarify. So one core issue has to do with the language definition itself. So in C++, there's actually a conceptual cycle between type propagation and alias analysis. In that one simple yellow text, if I don't know what the type of the pointer P is, then at compile time, I can't figure out what that call is to, and therefore I can't figure out what the effects are going to be on the alias analysis for A or B or anything that A and B contain pointers to. And then if it's difficult to find that what P's type is, it's probably because there were other pointers that aliased P. And so you can see the only way this cycle can be broken is at runtime. Here's the second core insight. This is an example of something we call secure by coincidence. It's secure because this program will run no matter what, and it's because of basically the implementation of malloc on the platform. So if malloc allocates things that are 0 mod 16 in size, and then you get a buffer of space that you're unaware of, and if you overflow that, your program will still run. In this particular example, the red less than or equal to in the header of the for loop is where the error is. We're going to write one more character. So if size is mod 16, the final write to local will corrupt stack data. Other cases will only read or write to malloc slop. This will only be observable if the following page is unmapped or not writable. And it will also be observable on the use of the corrupted data. All other cases are silent. So this is a platform runtime dependent issue right here. And this is another, if with alloc A, this is another really great exploit. Before I go any further, I want to acknowledge Google for creating the address sanitizer runtime. And I want to say a special thanks to Konstantin, who led the team at Google and has been very successful in taking the address sanitizer forward with fuzzing. It's been an amazing growth in the industry, and the address sanitizer really has become a de facto standard. So before I go any further, this is what I would say is a concise definition of memory safety. Now, all of this is documented on the MSDN page, and it's really complex. If you go into each one of these examples in a presentation that's this short, I'm going to leave you with the documentation, and a lot of these titles here will get you to examples on the MSDN page. And every one of these types of errors has source code as well as a Visual Studio screen dump. So the goal by using the address sanitizer is that there are no memory safety bugs left in your application, but it's always done with 0 false positives. If this thing finds a bug, it's probably your fault. So this is what the Clang and LLVM output looks like on the command line. And I'm going to go back to the demo just to make sure everybody understood what I was showing. We took it to this step. And with this IDE innovation, what we did is we tried to change the debug experience. And we also tried to change the way people should report bugs because of these new crash dump files. You don't have to use words to describe anything. All you have to do is pass along one of these new snapshot files, and Visual Studio will actually rehydrate it just as I've shown on the screen. So here are some of the results, and we're just getting started. We went after open source. We found bugs in the Azure SDK, Boost, OpenSSL, and the Electronic Arts version of their STL. We found 0 days in Windows. We also have a continuous fuzzing team, which uses the address sanitizer and then puts your modules into a wrapper, which will randomize input continuously, looking for all the paths of execution to exploit. We found bugs in the the Visual Studio shell itself. We found bugs in the VS debugger. We use it on the front end, the back end, and the linker, and we found bugs across all of those. I went on site to a couple of customers and found bugs in their code. And right now, we are bringing up Office, which is a giant source base with a lot of legacy code, and it's difficult to successfully build. But we did a manual boot of Word, PowerPoint, and Excel, and we found one bug in each of them on startup. And after this talk, I'll be talking to the Office team about integrating this into their build and dev process. So we use ASAN and static analysis. They both find bugs. And what we're saying to you is that you should too. And that's about it for me. And if you have any questions for Sunny or I ended a little bit early just to make sure there'd be time.
Yeah, perfect. Thanks so much. Yeah, we got a few minutes for questions. So if you have any questions, make sure you're on Microsoft Learn TV, because we will not see any sent to YouTube or Twitch, and then drop them in the chat. So we've got one question here. When you load up a dump file in Visual Studio, do you have to manually make sure you're using the same code you used to compile, or is there some magic which will do that for you?
Yeah, you do. You have to have the debug symbols in the code. We're working on expanding that so that it's rad hardened. So with Git, it'll all automatically pull down the correct versions. Cool.
And then a couple of questions which Gabor did answer, but I think would be interesting for the video is if you are trying to introduce these analysis tools into a large existing code base, what would be your tips?
Well, I can speak for the address sanitizer, and the address sanitizer is done so that you can do it a step at a time. The only prerequisite is that the C++ file that contains main has to be compiled with the address sanitizer flag so that the runtime can get ahead of everything in your application to hook all of the allocators. After that, you can run other modules that haven't, with that, or libraries that have not been compiled with the address sanitizer, and that's because a lot of the shadow bytes that we use, and I didn't have a chance to talk about that, will, quote, fail open. In other words, it doesn't require everything to be compiled with the address sanitizer on. And Sunny can speak to the static analysis.
Sure. For static analysis, I would say the first and foremost tip for a large code base is to grandfather existing warnings so that developers only get to see what they're working on. There's a lot higher reaction to the warnings when you're working on a PR, for example, or making a code change. So showing relevant warnings, not including warnings from external components, not including warnings from pre-existing code, legacy code, definitely increases the chance of these warnings getting attention and getting fixed. So I would say, and also having these warnings show up at every point in the developer workflow, whether you're just writing your code, or you are compiling, or you are even when you spin off a PR. I think at every point in your dev workflow, we got to have these checks, and we got to show you the relevant warnings. And with that, we have seen people pay more attention, and issues get fixed, as opposed to code gets checked in, and after 30 days you find bugs. I think people forget it's not in their top of the stack, and so we have seen the former approach to be a lot more effective.
Cool, thanks. All right, so there's a few more questions in chat, but we're pretty much at the end of our time here. So Sunny and Jim, if you want to hang around and answer those questions in chat, I'm sure people would appreciate that. And we're going to move on to the next talk. So thank you so much for joining us and giving us your expertise.